Salt melts ice, everybody knows that. You put salt on the driveway in winter, the ice disappears. You toss salt into the bucket when you're making ice cream, and the temperature drops. Salt melts ice. It's obvious. You learned it when you were 8 years old, and nobody ever corrected you, because why would they? It works. You've seen it with your own eyes 1,000 times. That's completely wrong, and I can prove it. See, I love a good wrong answer. Not because I enjoy catching people out. No, I love a wrong answer because it usually means the real answer is far more interesting than anyone expected. And this one, oh, this one is a beauty. Because what actually happens when salt touches ice is so much stranger, so much more subtle, and so much more revealing about how nature really operates, that once you see it, you'll never look at a glass of ice water the same way again. So let me take you through it, slowly, carefully, and by the end you'll understand something not just about salt and ice, but about one of the deepest ideas in all of physics, equilibrium. The quiet war that's always happening right under your nose. Let's start with what everyone thinks is happening. You sprinkle salt on a chunk of ice. The ice starts to disappear. Liquid water shows up where solid ice used to be. So naturally you conclude the salt melted the ice, as if the salt reached in there with tiny little hands and pulled the ice crystals apart, as if salt is some kind of anti-ice weapon, some hot energy source that just dissolves frozen water on contact. And I'm not saying the people who think that are stupid. They're not. They're being perfectly sensible. They see salt go on. They see ice come off, cause and effect. What else would you conclude? But here's where it gets interesting. Let me ask you a very simple question, the kind of question that sounds almost too simple, and that's exactly why most people skip right past it. What was happening to that ice before you added any salt at all? Think about it. You've got a block of ice sitting outside on a winter day. The air temperature is right around the freezing point, let's say 0 degrees Celsius, 32 Fahrenheit. What is that ice doing? Is it just sitting there, frozen solid, completely inert? No, absolutely not. And this is the key to everything. That ice is not just sitting there, it's doing something extraordinary. It's melting and freezing at the same time. And right at the surface of that ice, where ice meets the air, where ice meets a thin film of water, there's a battle going on. Water molecules on the surface of the ice are shaking loose, breaking free of the crystal, becoming liquid. That's melting. But at the very same time, liquid water molecules near the surface are slowing down, locking into the crystal lattice, becoming solid. That's freezing. Both processes are happening simultaneously. Right now, every second, on the surface of every piece of ice you've ever touched, at exactly 0 degrees Celsius, these two rates are equal. The rate of melting equals the rate of freezing. For every molecule that escapes the crystal, another one joins. The ice appears to be doing nothing, but it is furiously busy. It is a war that's perfectly balanced, a draw. This is what physicists call dynamic equilibrium, and it's one of the most important concepts in all of nature. And it is not just in ice, everywhere. When something looks like nothing is happening, it very often means that two opposite things are happening at exactly the same rate. Not stillness, balanced motion. The calm surface of a lake doesn't mean the water isn't moving. It means the wind pushing one way and the current pulling another have reached a temporary truce. A cup of coffee sitting on your desk at room temperature looks perfectly still, but molecules of water are evaporating off the surface every second, and molecules from the humid air are condensing back in. If the rate matches, the coffee level stays the same. Is the coffee doing nothing? No, it's doing everything at once. You just can't see it because the books balance. Now, I want you to hold that picture in your mind. Two opposing processes, melting and freezing, running at the same speed. A perfect tie. Because what salt does is not what you think. Salt does not melt the ice. Salt cheats. It rigs the game. But before I show you how the cheating works, I need to tell you something about ice that almost nobody knows. Something Michael Faraday figured out way back in 1842, and that scientists have spent the next 160 years confirming with every tool they could invent. Faraday noticed something peculiar. When you press two pieces of ice together, even in a cold room, they stick. Not because they're wet in the usual sense, not because of some adhesive, but because they fuse. They freeze together at the point of contact. He thought about this for a long while, and he proposed something radical. He said, the surface of ice, even well below the melting point, is not entirely solid. There is a thin liquid-like layer, just a few molecules thick, coating the surface of every piece of ice. At the time, people thought he was a bit crazy. How can a solid have a liquid layer on it below the melting point? It offends common sense. Solid means solid. Frozen means frozen. But Faraday was right. We've since confirmed it with X-ray scattering, with neutron diffraction, with atomic force microscopy, with some frequency generation spectroscopy, with computer simulations running billions of calculations. The surface molecules of ice are undercoordinated, meaning they have fewer neighbors to bond with than the molecules buried deep inside the crystal. They're less stable, they jiggle, they partially melt. Scientists call this surface pre-melting, or sometimes the quasi-liquid layer. And it happens on ice starting at temperatures as stunningly low as minus 90 degrees Celsius. Even at that brutal cold, the very outermost molecules on the surface of ice are disordered, liquid-like, breaking the rules of the rigid crystal beneath them. As the temperature rises towards zero, this layer gets thicker. More molecules participate. The liquid jacket grows. So even on a cold winter day, your ice cube is wearing a thin liquid coat. Tiny, almost immeasurably thin at low temperatures, but it's there. And this liquid layer is critically important because it's the arena where salt will do its dirty work. All right, so here's the full setup. You've got a piece of ice at 0 degrees. Its surface has this thin film of liquid water. Inside that film, melting and freezing are balanced perfectly. Every molecule that breaks free from the crystal, another one goes back in. The ice stays the same size, the water stays the same volume. Equilibrium. A perfect invisible stalemate. Now you throw salt on it. What happens? The salt doesn't touch the ice directly. Not really, it can't. The salt lands on that liquid film and immediately begins to dissolve into it. Sodium chloride breaks apart into sodium ions and chloride ions. Each grain of salt produces billions upon billions of these ions, and they float around in the water layer like tiny intruders at a very organized dance. And those ions don't do anything to the melting rate. This is crucial. This is the part you must not miss. The ice underneath keeps losing surface molecules at exactly the same rate it was before. Melting continues unchanged. The ice crystal doesn't know or care what's dissolved in the water above it. It shakes molecules loose at the same pace it always does. The energy required to break a molecule free from the lattice hasn't changed. The temperature hasn't changed. The crystal structure hasn't changed. Melting goes on, oblivious. But freezing? That changes everything. For a water molecule to freeze, to join the crystal, it has to find the right spot on the lattice. Picture it at the molecular scale. A water molecule drifting through the liquid comes near the ice surface. It needs to approach at the right orientation, slow down enough, and lock into the hexagonal pattern. When the water is pure, there's nothing in the way. Molecules drift toward the surface and click into place like tiles in a mosaic. The crystal grows as fast as it shrinks. But now the water is full of sodium and chloride ions. They're in the way. They're cluttering up the space near the crystal surface. Not because they're doing anything aggressive, not because there's some chemical attack going on, but just because they're there, occupying space, getting between the water molecules and the ice surface, bumping into water molecules that were heading for the crystal, and knocking them off course. Think of it this way. Imagine you're trying to park cars in a parking lot, and someone has scattered traffic cones all over the lot. The cones don't destroy the parking spaces. The spaces are still there. But good luck getting a car into one when there's a cone in the way, or a cone blocking the entrance lane, or 3 cones clustered right where you need to turn. It's not impossible, but it's slower, much slower. The result? Fewer water molecules manage to refreeze per second. The freezing rate drops. And here is the entire trick, the melting rate stays the same. So what happens when melting continues at full speed, but freezing slows down? You get a net loss of ice. More molecules leave the crystal than return to it. The ice shrinks. Liquid water accumulates, the puddle grows, and you standing there on your driveway with your bag of rock salt say the salt melted the ice. But the salt did no such thing. The salt slowed down the freezing. The melting was always happening. It was happening before you added the salt. The ice was always trying to destroy itself, molecule by molecule, shaking apart at the surface. It's just that before the salt arrived, the freezing was fast enough to keep up. The crystal was rebuilding itself as fast as it was falling apart. Salt tipped the balance. Salt sabotaged the reconstruction crew while the demolition crew kept working at full pace. That is such a different picture from salt melts ice. It's not just a different way of saying the same thing. The distinction matters because it reveals how nature actually operates at the molecular level. Nothing reaches in and destroys the ice. No force, no heat, no chemical reaction tears the crystal apart. The crystal was always tearing itself apart. Salt just kept it from healing. Now you might say, fine, Feynman, that's a clever distinction, but who cares? The ice still goes away either way, and you'd be right that the practical outcome is identical. But understanding the mechanism, the real mechanism, lets you predict things you couldn't predict otherwise. And predictions are the currency of physics. First prediction. Why does salt stop working below a certain temperature? People who spread salt on roads know this well. Below about minus 21 degrees Celsius, roughly minus 6 degrees Fahrenheit. Regular table salt is useless. The ice just sits there, stubborn as a mule, completely unimpressed by your sodium chloride. If you thought salt was actively melting ice, this would be a genuine mystery. Why would the melting power just cut out at some temperature? What changed? Did the salt get tired? But if you understand the real mechanism, the answer is obvious. At very low temperatures, the melting rate drops. Way down. Ice molecules have less thermal energy, so fewer of them have enough oomph to shake free from the crystal per second. The demolition crew is working in slow motion. Meanwhile, the freezing rate also drops because the salt is still gumming up the works. But even a reduced freezing rate will eventually catch up to a drastically reduced melting rate. At minus 21 degrees Celsius, even with the water completely saturated with sodium chloride, as salty as it can possibly get, the melting rate has fallen low enough that it matches the reduced freezing rate. A new equilibrium is established. The ice stays put. The war is balanced again, just at a lower temperature. This is called the eutectic point, and it's a specific, measurable, predictable number. Not a guess, not an approximation, a direct consequence of the physics. That's a prediction you can only make if you understand the real mechanism. And it turns out to be exactly correct. Second prediction. Why does the ice get colder when you add salt? If you've ever made ice cream the old-fashioned way with a hand crank and a wooden bucket, you know this trick. You pack ice around the cream container, throw in a bunch of rock salt, and the whole mixture drops well below zero. The ice actually gets colder as it disappears. If salt were adding energy to the ice, forcing it to melt, pumping heat into the crystal, the temperature should go up, not down. That's the opposite of what you'd expect from a melting agent. But it makes perfect, beautiful sense when you see the real picture. So salt disrupts freezing. Melting continues, but freezing can't keep up. Now, melting is an endothermic process. That's a fancy word that just means it absorbs heat. It takes energy to pull molecules away from the crystal. You've got to break those hydrogen bonds, and breaking bonds costs energy. Normally, freezing releases exactly that much energy back. A water molecule locks into the crystal, new hydrogen bonds form, and energy is released as heat. When melting and freezing are balanced, the heat absorbed by melting equals the heat released by freezing. Temperature stays constant. But now melting is winning. More molecules are breaking free than locking in. More bonds are being broken than formed. That means a net absorption of heat from the surroundings. The ice and the water around it actually get colder. The temperature drops. You've created a situation where the ice is sucking heat out of its environment faster than freezing can put it back. Energy is being consumed with no compensation. This is not a minor detail. This is how people made ice cream for hundreds of years before electric freezers existed. You can get a salt-ice mixture down to minus 20 degrees Celsius or even a bit lower. That's well below the freezing point of cream, and it works not because salt is hot, but because salt lets melting run away while freezing can't compensate. The heat gets pulled right out of the cream and it solidifies into something delicious. Third prediction. Why should it matter what kind of salt you use? Cities sometimes switch from sodium chloride to calcium chloride when it gets really cold. Calcium chloride works down to about minus 50 degrees Celsius, a much more impressive number. Why? Both are salts. Both dissolve in water. What gives calcium chloride the advantage? Because calcium chloride splits into 3 ions when it dissolves, not 2. 1 calcium ion and 2 chloride ions. That's 50% more obstacles in the water for every molecule of salt you dissolve. More ions means more disruption to the freezing process. The freezing rate gets knocked down even further, which means the imbalance between melting and freezing persists to much lower temperatures before a new equilibrium is reached. This is what chemists call a colligative property. And colligative is just a Latin-derived word meaning depending on the collection. The size of the effect doesn't depend on what the dissolved particles are, not their charge, not their size, not their chemistry. It depends on how many of them there are. Period. Sugar would work too in principle. You could dump sugar on ice and depress the freezing point, but sugar doesn't dissociate into ions. 1 molecule of sugar gives you 1 particle in solution. 1 molecule of sodium chloride gives you 2. 1 molecule of calcium chloride gives you 3. More particles, bigger effect. More traffic cones in the parking lot. And this connects to something much broader and more beautiful. The whole phenomenon, this freezing point depression, is just one example of what happens when you disturb a system at equilibrium. There's a wonderful principle in thermodynamics, first clearly stated by Henri Le Chatelier in 1884, that says if you disturb a system at equilibrium, the system will shift in a way that partially counteracts the disturbance. Add something that slows down freezing, fine, says nature. I'll lower the temperature until freezing speeds up enough to match melting again. The equilibrium point moves, but it doesn't vanish. Nature always finds a new balance. Always. You push, and the system pushes back. Not hard enough to undo what you did, but enough to partially compensate. It's as if the universe has a deep, unshakable commitment to compromise. You see this everywhere, once you know what to look for. Squeeze a gas, and it heats up, partially resisting the compression. Heat a reaction mixture, and the equilibrium shifts toward products that absorb heat, partially counteracting the temperature rise. Add ions to water, and the freezing point drops, creating a new state where melting and freezing can balance again despite the intruders. Le Chatelier's principle isn't a law in the strictest sense. It's more like a consequence of thermodynamics, but it's one of the most useful thinking tools ever devised. I think there's a lesson in all of this. Not just a physics lesson, a thinking lesson. We look at things and we see the dramatic event. The ice disappearing, the road clearing, the temperature plunging, and we instinctively credit the most obvious actor, the salt. But the real action was happening before the salt ever arrived. The molecules were already in motion. The equilibrium was already a battlefield. Salt just changed the rules of engagement. This happens all over physics. The thing you see is usually not the thing that's actually happening. The ball falls and you think gravity is doing all the work, but really the ball was being held up by a force that just stopped. The star explodes and you think some catastrophic trigger set it off, but the fuel ran out and gravity, which was always there, always pushing inward, always patient, finally won. A dam breaks and you say the water burst through, but the water was always pressing. Every second, the dam just failed to hold. Over and over, the visible event is the failure of a balance, not the introduction of a new force. And that's exactly what happens with salt on ice. The visible event, the melting, is the failure of freezing to keep pace, not the arrival of some new melting power. Let me leave you with one more thought that I find particularly delicious. Remember Faraday and his liquid layer. That observation from 1842. the one where everyone thought he'd gone soft. It turns out that liquid layer is the primary reason ice is slippery, not pressure melting from your boot or your ice skate the way they taught it in school for decades. That explanation doesn't actually hold up. The pressure under an ice skate blade is nowhere near enough to melt ice at typical skating temperatures. You'd need pressures far greater than what a skate blade produces. And besides, ice is slippery even when you're just standing on it in sneakers, applying almost no pressure at all. No, the real reason you slide on ice is that the surface of ice is already wet. It was wet before you stepped on it, before anyone stepped on it. Since the moment the ice formed, the molecules on the surface are always a little bit loose, a little bit liquid, always in that partially melted state because of their undercoordination. That built-in lubrication, that molecular thin layer of disorder, is what makes the whole thing slick. So the next time you slip on the ice as you're windmilling your arms and wondering where your dignity went, take comfort in this. You're not just clumsy. You're experiencing a consequence of surface energy minimization at crystalline interfaces, first predicted by Michael Faraday over 160 years ago. It's a profound phenomenon. Though I admit that knowledge may not help you much on the way down, the world is full of things like this. Simple, familiar phenomena that everyone thinks they understand that turn out, on closer inspection, to be operating by a completely different mechanism than the one we imagined. And that deeper mechanism, the real one, is almost always more interesting, more elegant, and more useful than the story we made up. Salt does not melt ice. Ice was always melting. Salt just stops it from freezing back. A small distinction, you might think. But I believe small distinctions are where all the good physics lives. The universe doesn't hide its secrets behind complicated mathematics or expensive equipment. It hides them behind assumptions so obvious that nobody bothers to question them. So here's something to turn over in your mind. What other everyday things do you explain with the wrong mechanism? What else are you seeing the surface of while the real action is somewhere deeper, hidden in an equilibrium you never knew existed? I'd be very curious to hear what you come up with.